All page components are present in the Pages folder. Index has a page component that specifies a root URL. The router component will look for that when it tries to match the browser URL with the page. When I start the application, the initial URL will be at the root level. The router will match that with the index page and render it. When I go to /create, a page with the /create page directive will be rendered. Back in the index page component, there's also a code block in which the products collection is declared. Notice the for each statement that iterates over it. In the method onInitializedAsync, the products are fetched from the repository and put into the property. The repository is injected using a special inject directive. OnInitializedAsync is a handler for a lifecycle event. It is called by the Blazor runtime, in this case when the component is first rendered. Before the data is fetched, the list will be empty, and the page will also show that, very briefly. So brief in fact that I cannot show you. As soon as the products are loaded, the page will list the products. The products property is bound to the visible list of products using one-way data binding. When the property changes, the list will update automatically. The page will be re-rendered and compared with the old one. The browser will then be instructed to just update the parts of the page that were changed. This dynamic behavior is typical for single-page applications. After switching to the Create page, you can see that it indeed has the /create argument after page to instruct the router. In the markup, there is something that stands out. We're using components like edit form, input text and input number to render the form instead of using the normal HTML elements for these. And that's because these components support ASP.NET Core data validation, using the data annotation attributes present in the product class. The data annotations validator component will do the actual validation, and the validation summary will display model state errors automatically. Also notice that the inputs are bound to properties of something called newProduct. Using this syntax, the properties are bound to the input elements in a two-way manner. That means when the property changes its value, it will be reflected in the input, but also the other way around. Edit form also calls a method createProduct when the form is submitted without validation errors. newProduct and the method are not in the Razor file, but in a separate file that contains the code. This technique can be used to separate the code from the markup. The partial class is an addition to the class that is generated from the Razor. And there are the newProduct property and the createProduct method. Product repository and the built-in navigation manager are injected using the inject attribute. createProduct then adds the product to the repository and uses the navigation manager to redirect to the root URL, the list of products. Keep in mind that this won't generate a server request. Instead, the router will do its matching and show the correct page, all from within the browser. To show you how custom components work, I've created a logo component that just renders the logo using a certain height. It can be found in the Components folder. In the IMG HTML element, I reference a property called height. The parameter attribute indicates that it can be set by another component. In the main layout.razor file, I'm using the custom logo component, providing a value for the height property. Now that I have this separate logo component, I can use it anywhere in the application, using different heights if needed. Blazor Server is another way to create Blazor applications, without the need for WebAssembly. I'll explain in the next clip. As soon as a Blazor Server application starts, it will establish a two-way communication connection that remains open as long as the application is used. Blazor uses another ASP.NET Core technology for this, SignalR. A framework that makes such a two-way connection possible using web techniques like WebSockets. Initially, the landing page will be rendered by the server, and the browser will get the resulting HTML. The server will be notified of all user activity, such as navigation to other pages or submitting data. It will process the user's activity and it will take care of sending new HTML over to the browser. But just the HTML that was updated. Using this technique, the user will get the same single-page application experience as with Blazor WebAssembly. The state of the application is still kept on the browser, and that's probably why this is still regarded as a client-rendered application, even though the actual rendering is done on the server. Let's take a look at the Blazor server application. The good news is that every component I showed you in the Blazor WebAssembly application is exactly the same here, so I will not show them again. I'll just mention the differences between the projects. ProgramCS uses the builder for a server-rendered application and adds the Razor Pages classes to the dependency injection container to render the pages as well as some extras for Blazor Server. There's middleware that makes sure the SignalR hub is mapped to a URL. A SignalR hub is a class that enables the two-way connection. When a non-SingleR request comes in, such as the very first request, the _host Razor page will be rendered. The page renders the app root component using a tag helper. And from the app component onwards, the application is exactly the same as I showed you, except for the fact that the _layout.cs HTML layout page now contains the outer HTML structure and loads a JavaScript called Blazor Server.js, which will maintain the SignalR connection. If you have one more minute for this module, I'll compare Blazor WebAssembly and Server in the next clip. We're comparing the two hosting models. APIs aside, with Blazor WebAssembly, the server has to serve some files on the initial request and it's basically done. With the server version of Blazor, the server has to do most of the work. And because the processing with WebAssembly is done in the browser, on the user's machine, scaling is very cost effective. When applications have many users, scaling out with Blazor Server could get expensive. And we saw that initial loading times are longer with WebAssembly. There's no such problem with Server. Because all UI processing is done in the browser once loaded, the application can keep on functioning. For the UI to function, it is server independent. This enables scenarios where the application can be used offline. For Blazor Server, the application doesn't function without a server connection. And that's also a vulnerability. If somehow the permanent connection cannot be kept stable, it could lead to unexpected behavior. And finally, we're bound to what the server can do in WebAssembly, where in Blazor Server we can use everything we know and love in .NET. Entity Framework, for example, is used a lot in .NET to access databases. It doesn't work in WebAssembly, but it does on Server. Most of the time, however, it's a good thing to keep the logic around data provisioning and UI separated by creating separate back and front-end applications. In the next module, you'll learn how an API application is created with ASP.NET Core. ASP.NET Core is great for front-end applications, but also for back-end applications. Again, we have options. Web API and gRPC use two different patterns, and SignalR can also be seen as an API that supports server-to-client communication. But have no fear, by the time you finish this module, you'll know what to choose. I've already covered the basics on back-end APIs. But here's something I didn't tell you yet. An API has to be able to send and receive data. We use serialization for that. We're transforming C# objects into a format that can be sent over the wire. An example of such a format is JSON. The receiving end can then turn the serialized data into objects again using deserialization. Here's the new architecture of the application that includes APIs. When a server-rendered front-end is used, the browser will interact with the server to get the pages, as we saw. When data is needed, the server application will reach out to the API to get the data. When new data is introduced or altered, it will again contact the API to get it persisted and checked. With pure client-rendered front-end applications, such as Blazor WebAssembly applications, apart from the initial request, the server isn't involved with UI interaction. But it can't process data by itself, so it has to rely on an API for that. Now that we have the context, let's dig in with Web API. Web API in ASP.NET Core enables us to write REST-based APIs, also known as RESTful APIs. Typically in a REST API, the HTTP protocol is leveraged. We use HTTP requests and responses, and each piece of data is available on a unique endpoint. A list of products, for example, could be available at /products, and a product with an ID of 1 at /product/1. We use the HTTP methods, such as get, post and put, to determine what we want to do. A get is obvious, getting data. With a post, we introduce new data, and with the put, we update data. When the response comes back, we can examine the HTTP status code to see how it went. When getting data, for example, an HTTP status code 200 would indicate that everything went fine, and the data is contained in the response. A status code 404 would indicate that it couldn't find the data requested. Responses can also contain pointers in the form of URLs with suggestions on what to do next. When a new product is introduced with a post, the response could contain the URL on which to find the new product, for example. Web API can support other formats, but in the vast majority of cases, JSON will be used as a serialization format. This is also the default. A pattern that can be used to create APIs is using controllers. This is very similar to what we've learned when we looked at MVC. We have the C for controller and the M for model, but not the V for view, because APIs don't provide a user interface.